Okay, good morning, ladies and gentlemen. Thank you for coming at this presentation. He's Raúl Aragonés, and I'm Carlos Ferrer. We are members of AEInnova, and we will present a presentation with the title Power of Waste Heat. Okay, then we divided the presentation by in two parts. One is things that we already know, and the other we titled things that maybe you don't know. First of all, as you can see here, this is our planet, is the planet where we are living. And for the moment and for the future, it seems that there is only one possibility to continue living altogether, independently of the richest level of the gender of the place where we are being born. Finally, we have to maintain and to keep this planet for the future generations. From the very beginning, we have been trying to survive in a very extreme conditions, from the cold part of the planet up to the deserts. And in any case, we have tried to take the best by our continuation as a species in this planet. Then, following that, from the very beginning, we have used several discoveries and several evolution tools that permit us to be more efficient in order to take food or to take the survival in this planet. First of all, the discovery of fire, very far time ago, also tools, and finally, technology. Technology means this is one of the oldest wheel that has been found in UK, but with these materials, good metals, and some other ones, we have made different type of machines and different type of elements. And more important, culture. That includes languages, art, and some other things that permitted just to transmit this information generation after generation and then continue evolving. Then, of course, the first big point where there is a change was the discovery of agriculture and livestock farming. And with that effect, we changed a lot. We changed a lot because we were able to produce more food in a more efficient way than to collect in the forest directly. Secondly, we have settled, and at the end, we have created villages, and we have created also cities, and that produces a lot of effects. Then, with that, after 1,000 years of this step-by-step evolution, we have arrived suddenly to another change, very far time ago from these first changes. That has been the discovery of the steaming machine. With the discovery of the steaming machine, as you know, basically it has created industry. And then industry produces in a more efficient way different type of goods that could be able to be used by us. But in addition, it started to increase another effect that is pollution, contamination. And contamination, of course, at the very beginning started closer to these industry production areas. And of course, this conference is about that, how to solve this big problem. And in our case, we will see later that we try to solve some of this part for industry applications. Additionally, the amount of people has been increased, and in the cities mainly, it appears more population. Additionally, the change to work has been changed from the high-made system up to industrial production, and that makes also society changes. And finally, it appears good for everybody. In different moments and different steps, of course, not at the same time in all the areas of the world. Then it seems that we got it. And the people is apparently happy because they have different things that they want that solve a lot of problems in their life. Then in cities, mainly, they have been grown, and that produces different effects, that we need more lighting systems, more heating systems, more transportation systems, that just at the end it needs and requires more energy. And this is one of the effects. And the industry continues evolving. That means that it's more efficient, more industrialized systems, and partially it is producing more contamination, because at the end, this is part of the collateral effects of the industrial production. Then we got it really that some of the effects that I said to you a little bit before is that from the starting of the Industrial Revolution, as you know, there has been a exponential evolution of the number of people that lives in this planet. Then, as you can see here, actually we are just in this point, but at the very beginning we were a little bit less than 1 billion of people in this planet. This is something that produces some of the acceleration effects that I commented before. Then if you are more people, you need more goods, more energy at the end to survive in the same way of life. Then, I'm sorry, I go so quickly. Then, of course, the communications and the amount of people, I'm sorry, there is no appear the video in this transparency, but that means there is a lot of energy needed, a lot of transportation, and finally, the cities started to be, mainly the big metropolitan areas, a big nightmare for the authorities, for the population that is living there, because at the end, we have to solve how to manage this thing. And additionally, with the industry, the problem is the contamination, how to solve it. Of course, it has appeared some restrictions, some constraints that time to time has been taking some decisions that try to solve part of this problem in order to reduce contamination, but it continues appearing other problems to continue this evolution, as I was saying to you. Then, taking into account this graphic that is well known, that independently of the constraints, is continually growing the CO2 emissions, basically due to the fuels that we are using, the fossil fuels that we are using, mainly oil, coal, and gas. And this is something to be taken into account. Additionally, some other effects is the plastic. Plastic is a big problem that is well known, and how to reduce it for the future generations, because it takes a lot of time to be recollect or to be transformed in another products. Finally, it provokes a reduction of biodiversity, and also other effect is the reduction of amount of the increase of temperature associated with the industrial processes that produces desertification and the melting of the poles, with the reduction of drinkable water for the next generations. Then it seems so terrible. Then what we can do? Basically, there is one first solution that is just to take profit of the renewable energies. That is something that goes step by step. It's not easy to change from one day to other, but basically more than hydroelectrical energy that is very reduced and limited in some areas, solar and wind energy are two of the sources that is more well known and is starting to establish to every place, that permits us to continue being, in one way, to live in a comfortable way, as we have been living in the last generations, and secondly, to be more respectful to the environment. And why not? Here is another example presented some years ago by Solar Impulse, that is, you can extend this usage, if you apply it very well, to any type of transportation. Not only the electromobility, this is something that all the people that we have been working in this area, we know that electrical car is something that is coming. There is a lot of problems, but it seems that it will be part of the solution. and why not extend it to other methods of transportation. Then, what are the other things? My colleague will show you basically what are our part that we can help also to these improvements.
Thank you, Carlos. Well, now we're going to explain several things that maybe you don't know, but I think they're all related with energy efficiency. Well, first of all, Carlos, give me the pass. There are too many principles we want to pay attention. First of all, in the future, there will be several energies that will converge and will allow us to become a more sustainable society. All of them are needed, and all of them are complementary to achieve this goal. Like, in this case, our Catalan castles, well we know. The next, all the energy counts. We cannot discard any kind of energy, because many little makes a weakle. Well, if try to dip in the concept of energy harvesting, maybe you don't know what's the meaning of this kind of energy. Looking for directly inside the Wikipedia, we find this description. It's the process by which energy is obtained from external sources, like solar power, wind energy, thermal energy, kinetic, etc. Well, this is one example. These guys harvest energy from sea waves. Impressive how they do that. Another example, these guys harvest energy from footsteps. We can charge mobile phones, we can, for example, generate energy for lighting. So this is energy harvesting. It's an invisible energy, but it is there. So why not to take benefit of this kind of energy? In our case, we're going to dip in the energy harvesting from the waste heat. Let me give some important numbers. Only taking an example as Europe 28, practically the 21% of the all yearly energy needs of Europe is lost in this, in waste heat. 21%. That means more or less 15 nuclear power plants working at full power, and this energy is lost in the sky. Big industries, we'll dip later, deep industries lost up to 65% of their energy consumption in form of waste heat, just for transforming the raw materials into processed materials. So our solution will help them to become more efficient. And this energy loss is incredible. It corresponds to 1 petawatt hour yearly loss of energy. We cannot sustain this. Well, AEInnova was born in 2014 from the microelectronic department of the Autonomous University of Barcelona, like a spin-off. And our mission was to take technology from the space and use this technology here in the industry to help them to become more efficient. This project, heat recovery project, has been funded by the European Commission LIFE program. That is the excellence program of the European Commission, focusing on improving technology solutions for obtain a more affordable and environmental friendly climate. Here you say the first pilot has been installed in the market. It was in Volkswagen, SEAT, Spain in 2016. We will dip later in this technology, but now we have to identify that in Europe there are, as said by the European Commission, there exist 13 different industries that are what is called commonly high demanding energy industries that are the problem of the European consumption, the European loss in energy. Basically, in the European Union 28 members, these sectors corresponds to 1,820 terawatt hour of energy consumption yearly, And thanks to this project with the European Commission LIFE program, we will pay attention to basically 6 of these high energy demanding industries in detail, in iron and steel, chemical, non-metallic, food, drink, paper, and mining. We will develop 6 pilots in these 6 basic industries to demonstrate that the solution is suitable for this kind of industries. Here we have a little instruction about the solution, the explosion. You see that, for example, if you are taking any kind of chimneys, any kind of head pipes, any kind of furnaces, any kind of heat sources is suitable to use thermoelectricity as a method of conversion waste heat into electric power. In fact, this technology was used in 1970s by NASA Propulsion Laboratory with our Voyager spacecrafts, Galileo spacecrafts. When you are selling a satellite and a spacecraft far away from Saturn, the sun is not a way to power your satellite, your spacecraft. So you have to look for other additional technologies to give electricity to your equipment. In this case, they used a heat source and they used thermoelectric material. We're making the same approach, but not for the space, but for the industry. So with these thermoelectric materials are present in the market, and our electronics, we built a waste heat recovery system that incorporates 6 of these thermoelectric materials. We build this equipment, and we create an enclosure where we will fit all these elements inside this enclosure. Then we put a chimney, we install this ring, this enclosure, and we install all the modules inside this enclosure. Then this energy that initially were being lost in heat, like a smoke, is being harvested by this solution and is injected in this inverter and go directly to the grid of the company. So we are recovering part of this waste heat, creating negative carbon energy. Then finally, this inverter is monitored so the customer can in real time monitor what's going on with the process. So how many kilowatts hour we are recovering from this waste. Here we see another example. This is from Gavarro. Here the gases passes through this section, and every single of these modules generates 25 watt-hour of energy. So as much surface you have, more rings you can install, and more power you are harvesting from this process. The second goal, I think this is a very important question to analyze. Is in the mouth of everyone speaking about the industry 4.0, okay? But anybody thinks about what is the cost for the environmental of this digitalization? So, for example, when you're trying to digitalize a big plant, like big petrochemical, big oil plants, big refineries, they have hundreds of kilometers of pipes. If you have to invest technology for sensorizing using wired solutions, the investment is enormous. In fact, a single meter of wire in a big industry costs up to 70 euros per meter. So investment in wiring for sensing is highly costly. So it's practically impossible to digitalize a plant using wired solutions. We have an alternative, the wireless solutions. But wireless solutions has a big problem, the battery. That means that for every single device, you need any single battery. And if you have, for example, in a big industry, for example, let's take a little example of a big oil plant. If you have 20,000 wireless IoT devices, you will need to replace yearly 20,000 batteries. So the cost for the industries just in battery replacement is enormous, and the cost for environment is highly enormous because you have to take account what is the footprint and the carbon footprint of the batteries. Also, if we pay attention about the forecast from McKinsey that says that in 2025 there will be 5 trillion wireless IoT devices, I asked to myself, is there any lithium in the world to power these devices? Well, and finally, a very interesting thing to take account that all these devices send data. Let me make a little example. when you are, for example, sending a single email with just a few characters of text, this single mail has an equivalent footprint of 9 grams of carbon emissions. 9 grams. So imagine every day how many emails are you sending or you're receiving in your mobile phone, how many messages you are sending by WhatsApp, by Telegram, and think about the equivalent of carbon footprint that is emitted to the atmosphere thanks of these transactions. So if we multiply this value with 5 trillion of devices, 5 trillion, we're emitting yearly, just for data, just for digitalizing big plants, just 125 million of tons of carbon. So I think we have a key to help them to become more sustainable. But these values are amazing. First of all, we are obtaining lithium from undeveloped countries. And this is a problem, because just for obtaining lithium, we also need cobalt. Maybe you know that 30% of the lithium battery is cobalt, and they are obtaining from undeveloped and in conflict countries like Congo. And in the majority of them, kids are working on it to obtain cobalt. So I think we are responsible when you're using lithium batteries of that. Well, with this spirit has born the Indoi project. Has been financed by the Spanish government, the Centro de Desarrollo Tecnológico Industrial, the Ministry of Industry. This is the new battery that uses heat as source of energy. This battery has no any kind of lithium. It's not really a battery. It's a thermal converter that substitutes a battery from a process, and is, I think, it's an equipment that can last up to 30, 40 years with no maintenance. These projects won in the last IoT World Congress the award of the best innovative technology worldwide, thanks for suppressing batteries from the IoT devices. Here, we explain how it works. We are gathering temperature from any hot pipe. We apply sensors, any kind of sensors, thermal sensor, vibration sensor, steam leak sensors, whatever sensor, and a transceiver. This is very interesting to analyze because this transceiver uses what is commonly said edge computing. Edge computing is an acronym of a high computation device that instead of reading data from any sensor and send the data directly to the cloud, what does this device is it reads data from the sensor, it processes all the data, and only send valuable data to the destination. Only valuable data. So basically, we are reducing practically up to the 95% the total throughput of data sent, because system only send, for example, if you define, hello, you have to tell me where this and this and this alert happens. And system become warning in alert and analyzes the data, and when this event passes, informs to the destination that this event has passed. But this is not sending all the data to the cloud, because another question is, everybody is speaking about cloud computing, but do you know really the impact in cost of energy and carbon of the cloud computation? So it's hardly enormous. So if we can reduce this computation in the cloud and give benefit to Microsoft and Amazon, and we can do this computation inside the IoT device that uses a waste heat, we are not consuming for do this computation. We are more friendly, environmental friendly. Here we have the thermal battery, the IoT device, using long-range communications protocols, like LoRaWAN, like narrowband IoT, like LTE-M, the sensor, and the receiver, and the platform called the ABIS, where we monitor all the results of this equipment. This is the first equipment installed worldwide using this thermal energy source. This is a big compressor of a big oil refinery from Repsol in Puerto Llano, Madrid. This is a compressor. We're monitoring vibrations in real time. So this equipment reads from this accelerometer leads vibration, sends the data to the IoT device that is powered from this pipe that has an oil refrigerant. So we are harvesting heat from this oil refrigerant. We generate half a watt of power, and with this half a watt, We are giving energy to this IoT device, and we send this data directly to the customer's IT platform. So we have suppressed a way of measuring using batteries. And also, like this equipment has no batteries, it is compatible, it's compliant with explosive environments. So we can help them to digitalize, because lithium battery is not suitable. So you cannot digitalize big plants because lithium can explode, and this is a barrier, a problem with this kind of facilities. Well, finally, I want to give a special attention, a special thanks to LIFE program of the European Commission, the H2020 SEMA instrument, the CDTI, Banc Sabadell, Barcelona Activa, Acció from Catalonia, Orbital 40, Repsol Foundation, InnoEnergy, United Nations, UAB, and Salesians, that has given support to our project from the very beginning, from 2014, and our points of energy, our points of power to make a step forward. Finally, we have a little demonstration. We try to show how this equipment works, but like we have to burn a flame, we're not allowed to make this really demonstration. This equipment that converts waste heat, so we can apply heat sources by this point. Here in the middle, we have the thermoelectrical material that converts waste heat into electric power. And doing that, we are powering this fan that says COP24, we are welcome here, using energy harvesting. Like we have not the possibility to make this flame. We have to make a little video where we show how it works. And this fan is running. So it's quite simple, the demonstration. And this equipment has no moving parts. These materials has a very, very low carbon footprint. It's basically they are based in tellurium and bismuth, other core materials in the planet. So it has a very low footprint, and they have a warranty of life of practically from 30 to 40 years. In fact, in all your campsite fridges, they are based in thermoelectric materials. We are using the other principle, the reverse principle. Instead of creating cold and heat from the electricity, like the fridge, the portable fridge, we are using the Seebeck effect. That is this is the reversible process. We're applying heat and cold. We have to create a delta T. We are creating enough energy. Now, it is possible to any kind of big industries to harvest heat. And, well, we are open to look for different end users and to validate the solution. And nothing else. Thank you for your attention and for your time. Have a nice day.
Thank you.
If you have any question.
Please feel free to make any question that you want about our technology or the solutions for industry or for other applications.
Hello, good morning. Good morning, my name is David Munene. I'm with the Catholic Youth Network for Environmental Sustainability in Africa. I very much appreciate your innovativeness in harvesting energy. My concern is I have seen a lot of your presentations are targeted at large-scale industries, for example. Is there any chance that this could be applied affordably at the lower levels, for example, in the households?
Yeah, in that way, it's a good question. Basically, our company has been focused in industry. Of course, this is one of the applications, mainly because industry normally presents a very big difference of temperature, taking into account for the first line with waste heat recovery units. Basically, we started from a temperature higher of 200 degrees Celsius. But there is other type of applications that there has been examples also in your continent, in Africa, applying thermoelectricity from cooking systems to take some small amount of energy, like this example, in order to recharge batteries for mobile phones or for small lighting systems by LEDs. This is suitable too, if you have just enough difference of temperature. For the other application, as Raul showed you, basically in this case, with from 30 to 80 degrees Celsius of difference of temperature, you can start to, in this case, to have power supply for sensors. But for these other type of applications with 80 to a little bit more than 100 degrees Celsius, that in any cooking systems is easy to have at home in a lot of countries, this is suitable for these other alternative applications. Anyway, it's time to find the good market, the good way to develop this technology. And I could show you also these examples that has been a rise, and someone started to try also to give solutions to other sectors and other markets.
Hi, my name is Margot. I am a student researcher from the US, and I have kind of a two-part question. The first one is, don't know if you mentioned this, but out of the 65% of energy that is wasted in industry, how much does the battery capture? And where does the energy go from the battery that from the battery that the energy captured? So is it fed back into the system, or could you talk on that?
Okay, mainly up to now, thermal electricity has the capabilities to harvest energy from heat up to the 10 to 13%. So there are in the market, well, in research projects, you can find Peltier cells that can convert waste heat into electric power, achieving values up to 15 to 18%. But nowadays, in the market, you will see, for example, from Japanese Komatsu, from US HiZ, from California, San Diego, you can find thermoelectrical materials that can convert up to practically the 10% of this heat into electric power. In our examples, we have two big projects, two big verticals. The first one is the vertical heat recovery. The mission is harvest energy and to do not store anywhere. So it is directly converted to alternative current and is injected directly to the grid. So you are making self-consumption. As more heat you are delivering to the atmosphere, more energy you can harvest. This is a principle. As much surface you have to take account that every single molecule of this cools the gas. It cools the gas more or less 3 to 4 degrees. So you cannot pile up as much as you want, because you make condensation of the water, and if the gas has any kind of sulfur, you are creating sulfur acid. But in this case, you have to analyze in real time what is the temperature you have in the gas, and you can pile up as many as you can, avoiding to arrive to this condensation temperature. Regarding to the system for the IoT, it is not allowed to use batteries to store energy. So basically, we are storing the energy in capacitors, in supercapacitors. Many you know, but like lithium batteries have a life of about 1,000 cycles of recharging. Supercapacitors has a life of practically 1 million at least. So you have millions of cycles. In fact, maybe if you have old TV at your home, 40 years old TV at home, it has capacitors and it is still working. So we store the energy in the capacitors, and when we have enough energy stored in the system, we wake up the system, we make the process of the data, we acquire the data from the sensor, we process the data because the value is to reduce the amount of data sent via wireless, and finally, system at all time wake off. So this process will depend in the energy that we are generating. If we are only working with only 15 degrees Celsius above ambient temperature, you are generating few energy. So in this case, we have to wait more time to make the measurement. But this system has the value of the system is that you can pile up as many power generators as you want. So you can interconnect themselves 3, 4, 5 to increase this power and to obtain more real-time data in the measurement. Okay?
An additional point to this comment of my colleague. Basically, thermoelectricity, in comparison with solar and wind, it not depends in the weather, or if you are at night or in day because you have sun or not, you don't have sun or anything. Any time that you have a process that produces heat, that for industry is all the running time of the industrial process, or at home when you are cooking is all the time that your cooking system or your heating system is working, you have energy to be scavenging or harvested in order to transform it into electricity. Then you can store it in an alternative ways of storage that are less contaminant than other ones, and then when you have enough energy, you can use it. Only basically because RF transmissions requires the majority of the energy that is harvested because it's the more required one for your system in IoT applications. Then, of course, there are other type of applications, mainly for the smart cities, that typically solar panels has the more efficient way to supply energy for these systems. Then, in each one of the sectors and each one of the applications, you have to see. But the thing that we show is that there is any other alternative that has started to be competitive for a lot of markets that is available at this moment. Any other question? No? Then we can close, and thank you everybody for your attention to be here. And if you have any other question in the future moments, you can directly come to us and we will continue discussion with you. Thank you very much.